This afternoon we have with us Savatra Bhatt, who works with the IBM Linux Technology Centre. His previous work on the Linux kernel is concerned energy management. His present work is on redesigning the CPU hotplug infrastructure and making it more common across different architectures, which is the topic of his talk. Thank you.
Thank you. Hello. Can you hear me? Thank you. So I'll be talking about CPU hotplug and some of my work related to its redesign to improve its efficiency and the way it deals with the rest of the system. So this is what the agenda looks like. So I'll be giving a brief introduction to what is CPU hotplug and where is it used and why is it important. And then I'll give a brief overview of the design of CPU hotplug and something known as stop machine, which is a pain point of today's CPU hotplug design. And then I'll discuss my design for removing stop machine from CPU hotplug and thereby improving the performance of CPU hotplug as well as the workload latencies of the tasks running on the rest of the CPUs. And then I'll share some experimental results from my patches, and then I'll discuss some other issues that CPU hotplug faces today and what we can do about them. And then briefly touch upon what we have for the future and how all this work benefits the end user. Okay. So what is CPU hotplug? Literally it means plugging in and plugging out CPUs at runtime. If you split up the words hot and plug. But then then you get into the issue of, is it really, are you really physically plugging out CPUs or are you only doing it logically? So the thing is, even if you want to physically pull out CPUs, CPU sockets, at runtime, you'll have to tell the OS to get rid of all its dependencies on the CPUs, right? It would be running tasks and stuff. It has to save the state somewhere so that you can actually power it down and remove it out, things like that. So logical hotplug precedes physical hotplug, and as you can expect, physical hotplug nobody actually does it very frequently. I mean, it's very exotic, right? So, but logical hotplug is used in many cases, in many common cases. I'll come to that, and it's pretty useful. And basically, what it means is you tell the operating system to stop depending on a CPU. You basically don't use it anymore, or start using as if a new CPU just appeared out of nowhere, right? That's what it means in a simple view. So let's see what a hot online operation looks like from a scheduler's point of view. Initially, you perform the architecture-specific init sequence on that CPU as if the CPU is new, and then you enable interrupts on the CPU, and then you tell the scheduler that, hey, look, there is a new CPU you can actually use, and then it puts it into its data structures and start load balancing on that and sharing the workloads on that CPU. And effectively, at the end, it's like the CPU was always there. There's no difference. And the offline operation looks somewhat, the reverse of that. So CPU might have been running some tasks. You have to migrate them away to other CPUs, save the state somewhere, and then tell the scheduler that you're going to need that CPU to be offline. You don't want to use that anymore. And then don't use it for load balancing. And when you don't have anything to do on a CPU, right, you're not running anything, it can actually go to a low power idle state, right? So then you can choose to do anything you want with that. So that's the end of logical hotplug. Then you can physically power it down and pull it out or whatever you want. But then that low power idle state, that's the end of logical hotplug. That is a useful operation. I'll come to that. Why is it useful? So an offline CPU enjoys peace, basically. So you can have a CPU doing nothing and it will be idle. But then an offline CPU has some extra benefits in that it will never get interrupts, it will never have timers running, no wake up events from anywhere because the OS thinks that it's not there, right? And then any pending work was already migrated to some other CPU and there won't be any future work too, right? So it's basically doing nothing. It has a deep quiescent state. So this can be potentially used for long idle times. I'll come to that later. And one of the key things about CPU hotplug is that many kernel subsystems are involved, not just the scheduler. Usually we attach CPU with the scheduler and that's about it. But that's not true, because we have something called a CPU online mask. It's a bit mask of all the CPUs that are online. So when you do hot plug, the mask changes. You flip the bits. And there are many kernel subsystems that do a for loop on that mask and take actions based on that. So everybody who has to use that mask to take decisions or actions need to cooperate with CPU hot plug. It should be aware of CPU hot plug. And the latency of actually doing a hot plug operation is usually from around 10 to 100 milliseconds. But under high load, it can also go to a couple of seconds, which can be very bad to certain use cases, as I'll show in a couple of slides. So let's see. We discussed what is hot plug. Now let's see where is it used. As common operations as booting and shutdown use CPU hot plug today. Most SMP architectures do booting via CPU hot plug. So what happens when you press your power button is that you come with one CPU initialized and running your kernel. You'll have to transition from a uniprocessor to SMP configuration, and that happens using CPU online operation in the kernel. And similarly, the shutdown operation is the opposite. You switch off or take offline CPUs one by one, and then call the firmware methods to actually put the system to kill the power to the system. And then suspend, resume, and hibernation. This is even more frequent on embedded devices and smartphones and laptops. So that also uses CPU hot plug, because the firmware demands that because you're going to save power, and that means you're going to kill power to the CPUs. You got to save the state somewhere. Only the memory will be powered on during suspend, and in hibernation even that won't be powered on, right? So that requires that you move from SMP to UP again. You just have to save enough state so that you can come back. So that uses CPU hot plug framework as well. Then on power systems, there is an operation called DLPAR, dynamic logical partitioning, that also uses CPU hot plug. I have a slide that can show you in a much better way what that means. Basically, you do virtual CPU hot plug so that you can utilize your hardware better. And then for reliability, availability, and serviceability, basically RAS reasons. So if your CPU is faulty, you can switch it off. It asks the CPU to not use that anymore without actually bringing down your system, and without a reboot or anything like that. This is actually the first, pretty much the first application of CPU hot plug. Why was it designed in the first place? And for that, the latency doesn't really matter that much. But for the rest of the use cases, as you can see, it does matter. And then for power management, as I said, an offline CPU enjoys peace. So you can potentially have longer idle times, deeper idle states, so you can get more power savings. Ideally, the scheduler has to deal with that. It should be power aware and stuff like that. But then in certain circumstances, you might be tempted to use CPU hot plug for this as well. And there are some ARM platforms where you have some platform constraints to enter deeper idle states, like clustered idle and so on, where the constraint is that you can put individual CPUs to idle states, but that won't give you a lot of power savings. If you want to put a cluster of CPUs to idle state, there are requirements like that they should not get interrupts and things like that. So for that, the only way to ensure that is to actually take CPU offline, so that the OS won't interrupt it anymore, so that you can take the cluster to an idle state. So let me explain suspend resume a little more in detail, because that is what is the most heavily used operation that deals with CPU hot plug. So every time it's heavily used in laptops, smartphones, and stuff like that. So every time your screen goes blank, it actually goes to a suspend state. That's how you get your long battery life, right? So, and when you get a phone call, or when you touch your screen, it'll come back into, it'll resume from the suspend state. And as you can see in the suspend path, you have to freeze all your tasks in the same state that they were in, because on resume you want to come back to the same state. And then you invoke the device driver routines to put your individual devices to low power suspend state, and then optional platform specific hooks. And then finally you offline all non-boot CPUs. You save the state somewhere, migrate tasks, and things like that. And with one CPU on, you invoke the firmware methods to actually kill the power and put the system to suspend state. The reverse operation happens on resume. So as you can see, the highlighted part, as you increase the number of CPUs on your machine, that highlighted part takes longer and longer, right? So we already have multi-core smartphones. So the more CPUs you put into that, if this is, if the performance of this part is not good enough, then you won't be having enough power savings. Your suspend resume will become slower and slower, right? So this is why it's important to care about the latency of hotplug. This is dual power operations on power systems I was talking about. So basically, what this shows is a physical machine with processors, bunch of processors, P1 to P6, and then you have virtual server instances. And before dual power, as you can see in the color-coded scheme, there are two virtual server instances. One of them is lightly loaded, the other one is heavily loaded. V stands for virtual CPUs that map to physical CPUs. So what you can do is you can do a vCPU offline on the first virtual server and online a new CPU there, so that you can distribute the load properly and have better hardware utilization, right? This is another. So here you are not doing host CPU hotplug, you're doing guest CPU hotplug. Okay, now let's get into some design details of hotplug. So callbacks run and drive CPU hotplug. There is no monolithic function that will take CPUs offline or anything like that. The reason being, as I mentioned earlier, many kernel subsystems are involved. So everybody can register its callback. It can say, when you're taking a CPU offline, tell me, or rather invoke my function. I'll do something, some setup step for that to happen. And that's how it proceeds. And CPU hotplug is actually a state machine. It sends set of notifications like this. Basically, it calls callbacks of every kernel subsystem that is interested with these other parameters, like CPU up prepare, CPU starting, CPU online, and things like that. So for example, on CPU down prepare, you got to initialize your data structures or whatever to prepare for an offline operation on that CPU. So it actually looks something like this. You have a CPU hotplug core code that invokes the individual callbacks with the notification. And then, so as you can see, for example, scheduler has a callback that has been registered with CPU hotplug core, and it will do something. And that something is specific to the scheduler for this example. For example, it stops load balancing on that CPU in preparation to take that CPU offline. Similarly, say, for example, CPU frequency driver stops managing that CPU, and so on. And this doesn't happen in parallel. So you can actually roll back if some of the steps fail, right? If the scheduler says, no, I couldn't actually stop load balancing on that CPU, you abort the operation and you can roll back, right? This is how it happens. So as you can see, there is no code in the hotplug core that actually takes the CPU offline. It's these callbacks that actually drop the dependence of the OS on that CPU to 0, right? Part by part, you actually make that happen. So this is how it works. That's user space. You can actually try it on your laptops and desktops. You can echo 1 to the online file. That will bring a CPU online. If you echo 0, it will go offline. So what happens is, the very task that did that, it will acquire the CPU hotplug lock, which is a mutex, and then invoke the notifiers in succession. And then during CPU starting, you actually do the init sequence on the CPU and finally release the lock and your CPU is online. Similarly, the CPU offline operation happens something like this: CPU down prepare notifications, CPU dying, and stuff like that. One of the things to note here is that the CPU dying notifiers runs in the context of stop machine, the one I was mentioning earlier. I'll deal with this in more detail. So the thing to notice here is, when stop machine is running, every other CPU is running with interrupts disabled. They're basically spinning, which is a bad thing. So how this particular step looks like is shown in this. Doing CPU offline using stop machine. So stop machine, when you invoke a function with stop machine, what it does is it starts high priority per CPU stopper threads on every CPU, including this CPU. So what I'm depicting in this diagram is that I want to take a CPU offline, CPU 1, and you have a bunch of other CPUs on the system. So basically you run high priority threads on everybody, and then this CPU, the one which is actually going to go offline, waits for that particular synchronization point, where every CPU has come to that point, stop machine disable IRQ, and they're basically spinning with interrupts disabled. And then he runs the stop machine run part of the state machine and invokes the CPU dying notifiers mentioned here, this one. So all throughout this duration, the rest of the CPUs run with interrupts disabled, no matter how many CPUs you have, right? You might have 10 CPUs, 20 CPUs, all of them run with interrupts disabled. And as I mentioned earlier, the hot plug latency can be quite high, milliseconds, 100 milliseconds, or even up to a couple of seconds, and you're doing nothing. That's why it's called stop machine. Basically, the entire machine is stopped. No interrupts means no work done, right? And then you have a synchronization point after this, where you're done with hot plug. At this point, you're actually offline, and then the rest of the system will continue, okay? So this is a bad design, because stop machine is really bad for workload latency. You might be doing something important, you might be running a user space. Just to take one CPU offline, you stop every CPU on the system and basically do nothing for that entire duration. So this is what I try to fix. And to give an example of the bad effect of stop machine, this is what it looks like. I ran this on a Power 750 machine with 128 CPUs. This shows the number of online CPUs, not the number of CPUs I'm taking offline. I'm taking only one CPU offline, and I'm measuring the average latency, how much time it takes, right? So as you can see, it's actually lower the better, right? So it's in milliseconds. So as you increase the number of CPUs, the stop machine stage takes longer and longer, and you go to hundreds of milliseconds. And this is average latency, not the worst case latency. Worst case can go to a couple of seconds. And while all this is happening, the machine is stopped. No interrupts are being serviced. So my redesign of CPU hot plug without stop machine looks something like this. It doesn't depend on the number of CPUs. You put any number of CPUs, it's the same. To begin with, it's exactly half of what it takes on a usual operation, and better than that, it scales well with it's actually lower the better, so it's a latency. So any number of CPUs, you don't have to worry about your hot plug duration, right? And that doesn't use stop machine. So that's an incentive to see what is that design that replaces stop machine. So before that, let me get into some locking consideration. This is all about locking and synchronization. So let me get some terminology straight. So we have something called hot plug readers and hot plug writers. So if you do that echo 0 or 1 to that online file, you're actually doing hot plug. But there might be other cases where you're, say, traversing the CPU online bit mask, and you don't want hot plug to happen. You don't want that bit flip during that critical section. Those are the hot plug readers. They prevent CPU hot plug. There are APIs that can help you do that. Get online CPUs, put online CPUs. It's like a ref counting mechanism. But the point to note here is that it's a blocking synchronization. That takes a mutex lock, so it will sleep if it doesn't get the lock, right? But then, what else? So reader set locking is recursive. You can call that recursively, and until the ref count comes back to 0, the writer will not proceed. So there is a way to say, don't do hot plug when I'm doing something important. And yeah, writer side locking, only one guy can do a hot plug operation at a time. But the point to note here is that this is blocking synchronization, as in, you can't do this in an interrupt handler, for example, right? You can't do it with a spin lock held or things like that. So let me get into atomic synchronization, meaning what will you do if you cannot prevent CPU hot plug using get online CPUs? So before that, I need to explain what is preempt, disable, and enable. So Linux supports kernel preemption. So a kernel task can actually be preempted if you have something more important to do. And if you don't want that preemption to happen, you need to enclose your critical section with preempt, disable, preempt, enable. Those are very heavily optimized operations. They are CPU local. You can think of it like CPU local. I mean, it's like a per CPU counter being incremented and decremented. And hence, it's really, really fast. And the cool thing is, there is no lock held. You don't hold a lock to say, don't preempt me, right? That's a good thing. So on a first note, you might be surprised, why is this related to hot plug? This thing is, for atomic synchronization, you use stop machine at the writer. What that means is, you run high priority stopper threads on everybody, right? But if you do a preempt disable, what you tell the kernel is, do not preempt me. Don't run whatever else that needs to run, even if it is of higher priority. So that prevents that stop machine from taking effect, right? So what happens is the hot plug writer keeps waiting for you to come to that point, synchronization point, and you'll never allow him as long as you have that preempt disable, as long as you are in that preempt disable section. That's why this becomes effective, right? If you disable IRQs or if you do a preempt disable, effectively you stop machine, which means you don't allow CPU offline to happen. So that is the synchronization scheme, and readers, it's a very fast operation. No, it's the current scheme, right. It's the current scheme. It uses very fast operations. I think I covered all this. Stop machine provides heavy-handed atomicity, which basically means that you kind of blindfold every CPU and run whatever you want and then release them, right? Because you run high priority stopper threads. They don't even hold locks. So how do we get rid of stop machine then? So first we need to see what are we up against, right? So the good part of stop machine design is that the reader side is superbly fast, as well as there are no locking rules, because it's not a lock that prevents you to do hot plug, right? So no lock ordering rules and hence no headache. Very flexible nesting rules, and it's a heavily optimized per CPU local operation, right? So whatever is going to replace that part should also be at least close to that. Otherwise, you'll have significant performance hit. Also, many of these readers, what I'm talking about, and these readers are atomic readers. They cannot sleep, and most of them are interrupt handlers and things like that. So they're really hot paths. So you can't afford to make the reader side slow with your replacement. And some of the readers, like SMP call function, it calls. So SMP call function uses preempt disable, preempt enable, because it's a function that can run a given function on many other CPUs. You give a mask, it will go and run it there. It doesn't want to race with hot plug, so it does preempt disable, preempt enable. Now if I'm going to enforce new lock ordering around such an exported symbol, then I'm going to have issues converting the kernel over to the new model, right? Basically it will be impossible. So we don't want new locking rules. We want to be very fast in the reader side, and we need to be flexible. We need to have cool nesting rules. I mean, no nesting, very flexible nesting rules. So we can't use straightforward synchronization schemes like this, because say for example, this clearly separates out into a reader writer semantics. So why not use a reader writer spin lock? So the problem is, suppose you have a reader writer global lock to do this. What happens is, suppose you're not doing hot plug, like for example, we're not doing hot plug anywhere, right? So what happens is, you got to take that lock for read and release that lock for read on the very hot paths. And that happens even when you're not doing this, and that leads to a lot of unnecessary cache line bouncing, right? And the worst part is you get a bad system performance even when you're not doing CPU hot plug. So you cannot use global reader writer lock. But the beauty of global reader writer lock is that there is no problems with deadlocks. You won't end up in new deadlocks because you just have a lock. So it's pretty convenient. So the logical choice is to move to per CPU reader writer locks. What if we have per CPU reader writer locks and have a straightforward scheme, in the sense that if you're a reader, you take your local reader writer lock for read and go ahead, and the writer will take everybody's reader writer lock for write and only then proceed. The problem is that you'll get into new non-existent deadlocks. I have charts to show that if anybody is interested. You get into new lock ordering, circular locking dependencies between the entities, and that won't be a viable solution. So lock ordering, whenever you enforce new lock ordering, you cannot compete with preempt disable, right? So, and it'll basically become impossible to use this model. So I designed a new synchronization scheme that uses the best of both. So basically, global reader writer locks provide deadlock safety, but lack of performance in the hot path. Per CPU variables instead of per CPU locks, if you use per CPU variables or ref counts, reference counters, it provides performance. So what you do is you differentiate hot plug into two paths, fast path and slow path. Fast path means you're not doing hot plug, just like my laptop now, right? So all the critical sections in the reader side can use per CPU ref counts, right? In the fast path, you use the per CPU ref counts to keep track of your nesting depth of the read side critical section. And when you're actually doing a hot plug, you use the slow path, which is using global redirector locks, the beauty of which is that there's no deadlock problems. There's no circle locking, none of that will happen. And this is, you're going to do a dynamic synchronization switch between these two when you actually start a hotplug operation. Because
why are you not using eCopy update?
sorry?
RCU.
Yeah, RCU, the problem is the writer, these parts of the writer are atomic. You cannot call synchronize CAD at that point, but you can call it before that, right? If you call it before,
because CPU hotplug is a state machine, can you simply use an RCU grace period between the different phases of CPU hotplug? So the writer between essentially becomes delayed by RCU grace periods, and so the readers can remain basically preempted or whatever, or as simple as an RCU read unlock.
yes, but the problem is,
you get a higher latency on the output operation, but you keep not running stop machine anyway.
yeah,
Yeah,
that's true.
I've seen a decision on KML, and people aren't too happy with get a new loading primitive in the kernel. So
That's true. But the problem is, you cannot run synchronized CAD at this point because you cannot block at that point. So you can do it before that. But the problem is,
you run asynchronously.
as in
machine. So you run the notifier for prepare, you call RCU, and later on you run the dying notifiers.
yeah, that's what I meant. I mean, before dying notifiers, you can do a. You don't want to do a synchronized CAD. You will do RCU read.
You don't do a synchronized CAD. You do a delayed RCU callback.
Okay. But then the problem is with this one. Suspend resume gets slower and slower because on every hot plug you'll have to do a RCU callback.
We could do a bulk offlining. It's the same thing from the CPU.
The time it takes doesn't scale up. You can do it all in constant time because you can offline all the economic CPUs simultaneously.
Yeah, we could do bulk offlining. I mean, there's no fundamental impossibility to bulk offlining.
Sorry.
In which case you have only one grace period.
So, yeah, there is no fundamental reason why you can't offline in bulk. I mean, from a scheduler perspective, it's pretty easy. So that would mean you would have a single RCU grace period, which isn't too bad. I mean, your
right.
case, you were showing you were still about 10 millisecond latency. So that fits perfectly within the envelope of an RCU grace period. I'm just proposing that as an alternate solution in case you don't manage to get your new locks through, because I've seen on the list that there was a significant pushback on having yet a new locking primitive in the kernel.
Okay.
So
I thought of hot plug. I have actually mentioned bulk CPU hot plug as a future work. I mean, that can potentially speed this up and improve this. Yeah, that's a good idea. Yeah, that can help this. But then without that, it can potentially slow it down unnecessarily. Yeah. Where were we? Okay. Yeah. So this is how the pseudocode looks like. So instead of using preempt disable and preempt disable, preempt enable, in the new model you'll use get online CPUs atomic and put online CPUs atomic, and that will look something like this. As I mentioned, the fast path and slow path differentiation. If there is no active writer, you just increment your ref count and go ahead, and that's per CPU ref count. And then if you have a active writer, then you do the synchronization switch. You actually have not shown the synchronization switch there. There is some code involved so that you should be able to do that safely. But the essential idea is that if there is a hot plug writer active, then you take the hot plug lock for read. And similarly, on the writer side, what you do is, first of all, assuming that all the readers are using per CPU ref counts and the writer is coming active afresh, you'll have to tell the writers to switch to the redirector locks. So you signal all readers to switch and wait for them to switch, and then you actually take the hot plug lock for write, and then tell the readers to go back to their own scheme. I mean, their per CPU ref count scheme.
It's a heavily biased rebuttal, but it's not the first time we want something like that. And
the need for such a construct have been coming regularly, where we have something where we want the read lock all the time everywhere, and we write every 36th of the month, and every time we've essentially turned doing things differently using typically either RCU or kernel thread or something.
Yeah, there's actually something similar to this in the VFS right now for, I think it's protecting superblocks against unmount. We have some kind of similar heavyweight, heavy read bias lock. So you might want to take a look at that code and see if you can use the same locking scheme that they're doing.
Okay, thank you. And then, yeah, I already mentioned this. This is what it looks like. It doesn't depend on the number of CPUs, so it scales well. The latency is low, and yeah, that's about what I had with the new design. So these are some other issues and challenges with hotplug. Some of them solved, some of them unsolved. Creation of per CPU K threads on every online and destruction during every offline. This was a performance challenge, taking a long time. But then Thomas Gleixner solved it by introducing the K-thread park and park infrastructure. What it means is you don't destroy and create K-threads anymore. You just stop them and start them. It's already in mainline. And stop machine is bad, as I just explained, and it hurts workload latency. And this design, what I proposed, can solve that potentially. And there is also some problems with callback driven process. This entire thing is callback driven. So you don't have a global view of the ordering of things that happen, and you can potentially get the priorities and notifiers wrong. And there have been plenty of bugs in that area. So Thomas Gleixner proposed that we can have callback free CPU hotplug, in the sense that you just put all the code together and run it, so that you can actually have a global view of what is happening one after the other. But it's not been, I don't think he has posted code to do that. So this is what the future looks like. You can get rid of the latency problems of hotplug using the design I proposed. And then without callbacks, you can run hotplug for better reliability and look into the hotplug process. And then Thomas also proposed making the online and offline operations symmetric, which they are not today, so that you can have something like multiple stages of online and offline. One of the things is that people use CPU hotplug for power management sometimes, and that doesn't really go well with the scheduler community. So what he was suggesting is that if we have multiple stages of CPU quiescence, then we could potentially not do this heavyweight operation and make it ugly. So that can potentially help do power savings in a lightweight manner. And then, as here both of you suggested, you can do bulk CPU hotplug for faster suspend resume. And so the idea is that instead of, if you have to take 10 CPUs offline, instead of invoking the callbacks one by one, you send a CPU mask, so that you can do it at a time. And potentially we can use the RCU mechanism at that point to have a better way of removing stop machine. What else do I have? So end user benefits from all this. So on mobile platforms, you'll have better, faster suspend resume, and you don't have to care about,
you might want to explain to people what DLR is. Okay.
Yeah. Okay, so basically on tablets and mobile phones, even if you have more and more number of CPUs, as long as you have a scalable design for CPU hotplug, you won't have to bother worry about the speed of suspend resume, and you can potentially have faster boot and shutdown, especially with bulk hotplug or something like that. And then you can have better power savings with multiple CPU quiescent states. On server systems, you can do faster DL power operations. That's basically, as requested, this. Where is that? This one. So we can utilize your hardware better using vCPU hotplug. And for RAS, so one of the things is that you want to take a CPU offline, but then you don't want to hurt the workload latencies of the rest of the system. You can do that without downtime and without hurting latency. And then, of course, if you want to do power savings via hotplug, you can do it. And even if you have to take a couple of CPUs offline, you won't have to bother about how much it affects the rest of your system with stop machine gone. These are the references, some of them from kernel documentation and some papers. And these are links to my patches and discussions. As you can see, I've gone through a couple of iterations of this design. Each of them have been complete redesign of the synchronization scheme. We have tried multiple designs, and currently that's the 5th one, what I have, and the results for which I showed in the slides. And this is some other work related to hotplug that I've done previously. And I think that's about it. Thank you very much. Any questions?
And thank you. And we've got 10 minutes for questions, so I think this will be lively.
I just wanted to ask you your sort of future directions. You had bulk hotplug right at the end.
Yeah. I mean, I didn't actually. This doesn't have to be in order.
Okay.
I mean, yeah.
Yeah, I was just wondering if there was, because that conceptually seems like it would be easier to do right now for some, you know, except for maybe the impact on the code. But in terms of for power management or suspend, you just go offline all the CPUs now, please.
The question with how complex bulk will be is how many callbacks actually are registered, because if there is 200, they all have to be fixed. If there is a dozen, it's easier. So that's, I don't know, what
And the other thing is,
do we have today?
Oh, way too many, way too many.
Roughly, how many?
Hundreds of them, yeah,
Okay.
definitely.
Yeah.
And the problem is, it might be, you know, mechanical and trivial to fix them, but the problem is with reliability. What if you fail at that some point and you roll back only a few of the CPUs in the CPU online mask? Now you have only one CPU to take care of. If something fails, you roll back that CPU. But then if you have a mask, then reliability becomes a bit of a problem to roll back. So.
Well, I mean, so for all intent of purpose, the rollback would require the rollback essentially is a cancel or backup event coming in. You would have semantically to require that whoever comes back up that way to examine the online mask, because it might indeed not be the same. But I don't see that as being a fundamental problem, because you can't rely on the online mask anyway across a large amount of code most of the time. So. Yeah, okay. But it feels to me that the bulk thing is definitely something that can be pursued in parallel and a worthwhile thing to do regardless, orthogonally from replacing stop machine.
Yeah.
I don't know what the code would look like. It would have to be very different, I think.
Although if Thomas is going to manage to get rid of all the notifiers, then there's going to be some significant interaction between those two patch series, and it might be worth postponing this until after Thomas has got done wreaking havoc on an N100 device drivers that want to know about it.
The thing is, Tom loves patch series that touch about 300 million files in a kernel in one go, so we'll let him deal with that.
Well, it's how he keeps his patch sets rates so high.
Okay. Thank you for paying attention. Thank you.